Without that nonlinear activation, I don't care how many layers you stack, your whole beautiful network would just collapse into one single flat linear equation.
In the forward pass for any given hidden layer, let's just call it layer L, the network takes the output from the previous layer, multiplies it by a set of learned weights W, adds a bias B, and then wraps the whole shebang in an activation function. It starts right at the input layer with raw feature vectors and mathematically transforms them step by step until out pops your prediction.
But honestly, the real MVP here is the activation function. Things like ReLU or JELU, they introduce non-linearity, and this is absolutely crucial. Without that nonlinear activation, I don't care how many layers you stack, your whole beautiful network would just collapse into one single flat linear equation. But with it, a sufficiently wide hidden layer achieves what we call universal approximation, meaning it can mathematically approximate pretty much any continuous function out there.
If you stack way too many of these sequentially, you run right into the vanishing gradient problem. The mathematical learning signal just gets too weak as it travels backward through all those layers during training. Modern networks use skip or residual connections. They provide these really handy shortcut paths for the gradient to flow smoothly by just completely bypassing certain layers. Suddenly, there's no problem building those massive 152-layer architectures without the model totally collapsing on you.